things first. I am not one of you. I am a physicist. I'm a computer scientist, but I'm not an evolution biologist. I also, I hope, am not an idiot. I've got about 100 refereed publications in my field. I have 13 patents. I've finished a dozen graduate students. But I'm not an evolution scientist. So I don't know your language. I don't know what interests you. I spent the week trying to find that stuff out. I've gone to a bunch of talks, some of which I understood and some of which I didn't. I've spoken to a bunch of you, some of whom I understood and some of whom I didn't. I've learned a bunch of small things, and I'm going to come back to that. And I've learned three big things. The first big thing I learned, both chronologically and in importance, is how welcoming this community is to people who are not members of it. So thank you. Everybody who's interacted with me, thank you. The second thing I learned was that everybody giving a talk, as far as I could tell, everybody giving a talk here was incredibly nervous before they gave it. This is a good thing for me because it means you know how I feel talking to a bunch of complete strangers. And the third thing I learned was that you guys don't like thought experiments. This is a bad thing for me because as a physicist, I love thought experiments. And I'm about to tell you about one. So I hope you'll bear with me. The other thing that I noticed, I went to all these talks, right? And I saw all these graphs, and I'm used to seeing lots of graphs. What surprised me, you guys all use the same graph. It's like, I don't understand it. But for better or worse, I figured I should also use the same graph. So there it is, and I want to talk about this graph in a particular context. And the context is a bunch of baby sea turtles trying to get to the ocean. And the deal for, it sucks to be a baby sea turtle, right? The odds are just completely stacked against you. You're probably not going to get to the ocean. And if you pretend for a moment that that your success or failure is entirely based on genetic properties, what that means, well, this is terrible. So this graph actually extends into the region you can't see. What that means is that you have to be way on the thin edge of this curve in order to have a shot at survival. And what you guys do, well, you can't see the top either. There's nothing I can do about this. What you guys do is you look at the mean of the graph and you talk about, well, if the sea turtles, thank you.
Oh,
See there?
sorry.
Well, it's
No,
sort
wrong
of
way.
better.
Forward is better.
Yeah.
Forward.
There you go.
Yeah, now you just lose all the stuff down here.
Hang on.
So you talk about,
That's
No.
okay.
close
Sorry.
enough. You talk about if the mean of the curve moves, and in general it seems to be universal that to the right is better. If the mean of the curve moves, that's good for the sea turtles because more of them survive, and you look at genetic things and how they impact the mean, and you do things like you say if the number of individuals in the population times the change in selectivity is bigger than 1, then the mutation can be preserved, and so forth and so on. And really all I want to say today is you can look at more. So if the mean stays the same, but the standard deviation improves, that's actually arguably even better. Because the turtles are playing this game where they're trying to be all the way out on the edge, and a higher standard deviation is much more effective at getting you out on the edge than just a change in the mean. And in fact, a higher standard deviation is so much more effective that a higher standard deviation with a worse mean is arguably better for the turtles. And that's what I want to talk about. The single thing I really want to say is it's not enough to just look at the means of all these distributions. You have to look at the higher moments also. The second thing I want to say is you can't really imagine just changing the standard deviation. It's not clear what that means. And what I want to argue is that you really should be interested in something that I'm just going to call dp d sigma. And by that I mean the change in the probability of success attributable to a 1 standard deviation change in genetic factors. And what the turtles want is they want that to be bigger. They want to be able to move their probability of success away from 0 by being 1 standard deviation out of 2 or whatever they need. And the last thing I want to say is that there are single behavioral changes that, surprisingly enough, have global impact on dp d sigma, and I'm going to talk about some of those. So, what does it mean to change this dp d sigma? The idea is you want to maximize the change in the probability of success corresponding to 1 standard deviation of probabilistic difference. So here's an example, flocking. I'm going to argue that the point of flocking is not tactical. It's to ensure that when the falcon shows up, the falcon really gets the weakest member of the flock. 1 standard deviation, because of the flocking, becomes much more dangerous. The exact same thing happens with lions chasing zebras. They will pick off the weakest member of the herd. That's what the zebras want at some level, because it means that dp d sigma is going well for them. There's a famous joke about 2 hikers who disturb a grizzly bear. And one of them starts running, the other person starts lacing up his shoes, and the guy who's running turns back and says, "What are you doing? You can't outrun a grizzly bear." And the guy working on his sneakers says, "I don't have to outrun a grizzly bear, right? I have to outrun you." And I would argue that's why birds flock, that's why zebras herd, because their goal is to put themselves in an environment where dp d sigma is as high as possible. Turtles have this, they sort of pseudo-flock. They don't actually flock, but all of the clutches of turtles on a beach didn't have to hatch at the same time. By doing so, they ensure that the weaker turtles will get wiped out by the predators, which is at some level what they want, because it takes less standard deviations to survive in a situation like that. Lastly, even parental investment is sort of like that. So if you have a species where the parents invest in the offspring, that basically means that a parent will stand in the way for predators trying to get to the offspring. And if the predator kills the parent, the offspring dies, but so do all the offspring's siblings. So you have this sort of terrible situation where you can die not because you have lousy genes, but because your sibling has lousy genes. Well, if your sibling has lousy genes, your genes are at least suspect, so you have exactly the same thing happening. Just for having suspect genes, the probability that you live is significantly reduced, so dp d sigma is better, and you have another generic behavior that has this effect. And the last thing I want to say is that I did a bunch of simulations under as wide a set of circumstances as I could sort of imagine, and they bore this out. Now, having been to all the talks, it occurred to me that maybe I should tell you about those. As a physicist, you should never trust an experimentalist who's presenting evidence supporting a theory that he invented. So I'm not. But if you want to know, you can ask me. There's a flip side to this that I should at least mention, and that's the predator side. So the predators don't have it nearly as bad, right? They're going to survive the encounter with the zebras. And what that suggests is that they do not want to form large groups. Because if they do, then you have these deadbeat predators who are basically going to survive off the pickings of the better predators. And you really, it's sort of like academics at some level. What you really want is you want the inefficient predators just to die out. So what that suggests is that if you believe all this, it should be a consequence of it that predators shouldn't flock, and that's exactly what happens. Predators don't. There are wolves form packs, but those are for very clear and very well understood tactical reasons. You don't have these giant flocks, giant schools of minnows that people explain in these bizarre ways. Even like a big ball of minnows will be intimidating to a predator. I've read that, I don't believe it for a minute. I've interacted with enough predators to know that you just don't put them off that way. But they do have the property that they ensure that the weakest members of the school are the most likely to get picked off. So, I went to all these talks and I tried to figure out what you guys cared about. And if I haven't made a fool of myself yet, I'm about to. So again, please bear with me. I tried to think what of the stuff you guys talk about, what falsifiable claim could I make based on the ideas I'm talking about? And I came up with one. I have no idea if this is true or not. I think it's the kind of thing you guys like thinking about, and that's the following. Imagine that you have two populations, roughly speaking, of a single species, either because they've been connected recently to a common ancestor or because they actually are geographically split. If you look at the ones that are in the harsher environment, and everything I'm saying is right, it should be the case that you see more genetic variation in that population than in the population that's facing the easier environment. Like I said, I have no idea if this is true. I'm going to take the thing down and pretend I can say it, but that seemed to be the kind of question that comes out of this that might be of interest to you all. That's really all I had to say. First, it is not enough just to look at the means of these various properties in the populations you guys always consider. Second, I think dp d sigma really is the right way to look at this. You want to look at how impactful is a one standard deviation change in whatever genetic properties you're considering. And lastly, I think this is, from my perspective, the most interesting. There are single changes in behavior that can actually have global impact on this dp d sigma thing that I've been talking about. So that's all I have. If you have questions, I will do my best. And if you have no questions, I have questions for you. So you get the first turn. Yeah.
So in your simulations, which you haven't shown, so I'm asking, on what does evolution act on at the individual level or at the group level?
So when I did the simulations, I had, I basically, every generation got repopulated, and the individuals were recast, and the genetic property of the parent had some bearing, but not a huge bearing on the genetic properties of the kids, and all the interactions between the zebras and the lions were handled at the individual level. And then I would see how many, both what happened to the genetic properties of the zebras and how many of them survived to the next generation, and then I just propagated it out a bunch of generations and saw what the expected number of zebras was as a function of the impact of flocking. Did I answer your question?
Yeah.
Okay. Should I talk about that? Maybe.
It's relevant to your...
I know it's relevant, I just didn't know exactly what to say. I mean, my problem was I eventually decided that I could have done the experiment again and again and again until it produced the results I wanted, and then I could talk about those, but that would be cheap. So, it should be, the experiment should be done by someone other than me who has no bias. So, my questions for you. First of all, is this interesting? Now, if the answer is no, you probably can't tell me why, because I thought about it from your side if it were physics, and I could. But if the answer is yes, what am I supposed to do next? I want to keep doing this. I have a life. I can't become one of you. Please find me and tell me.